Hello, this is Truth Socrates. Welcome to a portrait of linear algebra. Our video today is about subspaces. Now, of course, way back in chapter 2, we saw the concept of a subspace of a Euclidean space, Rn. So, of course, today we are going to generalize that concept to a subspace W of an abstract vector space V. Okay, so this time I didn't bother to write down the addition and the scalar multiplication. It's all implied. We will look at some examples of naturally occurring subspaces, which we have seen in our last couple of videos. We will find the basis for a vector space or a subspace, and we will find the dimension of these vector spaces or subspaces. So I hope that you can still remember the definitions for subspace, basis, and dimension from chapter 2. But if you don't, you're in luck because the definitions are going to be very, very similar. All right, so let's start with subspaces. A non-empty subset W of a vector space V with addition and scalar multiplication specified is called the subspace of V if W is closed under vector addition and scalar multiplication. This means that for all W1 and W2 in the subset W and any real number K, W1 plus W2 should also be from the subset W, and K times W1 should also be from the subset W. So if these three conditions are met, it's non-empty and closed under addition and scalar multiplication, we say that W is a subspace of V, and we refer to V as the eigenspace for W. So speaking of remembering stuff, back when we were talking about Rn, we said that every subspace of Rn must include which special vector? The zero vector, 0n. Okay, so it should be the same for W. Why is that? Well, it's non-empty, so there's at least one vector W from W. Okay, capital W. So what can we do with this W? Well, we can multiply by any scalar. All right. How can we get the zero vector? Pray tell. We multiply by 0. Okay, so 0 times W. I'll steal this symbol over here. We know that that is the zero vector in V. Okay, so that is 0 V. Okay, so therefore, just like in Rn, a subspace of V should always include the zero vector of V. Okay, so speaking of jogging your memory, I hope you remember that when we talked about the 10 axioms of a vector space, we started off with the two closure properties. So we have closure under addition and scalar multiplication. And then we had, I think, commutative property and associative property. And then we had the zero vector. Okay, so we just found out, we just showed that the zero vector in V should always be in W. Okay, so W has a zero vector. What was axiom 6? The additive inverses, the negatives. Okay, so if a vector W is from the subspace, do we know if its negative is also from the subspace? Okay, well, we got the zero vector by a scalar product, so any chance that, magic, we can get the negative of a vector also using a scalar product. Gosh, what could balance this equation? I'm sure you know the answer. It should be times -1. Okay? And we said that since W is closed under scalar multiplication, -1 times W should also be in W. Okay? So therefore, additive inverses are also in the subspace. The rest of the 4 axioms are all algebraic properties. Okay, So remember, we had two distributive properties, we had an associativity property, and the unitary property. 1 times a vector is still the same vector. So because those properties are true in the ambient space V, they're also true in W. Okay? So what that says is that a non-empty subset W of V is a subspace of V, if and only if W is itself a vector space, also under the same addition and scalar multiplication. All right, more trips down memory lane. In chapter 2, we said that there are two trivial subspaces of Rn. So similarly, if V is any vector space, there are two very trivial, very easy to understand subspaces of V. So there is the subset consisting of only the zero vector. That's closed under addition. Add the zero vector to itself, you get the zero vector. It's closed under scalar multiplication. You multiply the zero vector by any scalar, it's still the zero vector. Okay? But of course, V is also closed under vector addition and scalar multiplication. So V is itself a vector subspace of itself. Okay, it almost sounds ridiculous. But in mathematics, we allow sets to be subsets of themselves. Okay, so therefore, V is allowed to be a subspace of itself. But as I said, these are trivial. Okay, so are there more interesting subspaces? But of course. Okay, so back in chapter 2, we said that the span of a set of vectors is a subspace, and in fact, every subspace of Rn can be written as the span of a set of vectors because every subspace of Rn has a basis. Now, of course, we saw that word at the beginning of the video, and yeah, that's coming real soon. Okay, so for now, if you have a subset V1 through Vk from V, and you make the span of that subset of vectors, call it W, then that W is a subspace of V. And the proof, of course, is exactly the same. If you have a linear combination like C1V1 plus C2V2 to CKVK, and then you make another linear combination like D1V1 plus D2V2 through DKVK. You add them together, the commutative property says you can rearrange the terms. The distributive property says that you can factor out the two scalars. So you will get V1 times the scalar C1 plus V1. Okay? And so on. And of course, the same thing, similar thing happens when you multiply a linear combination by a scalar. That scalar just distributes to every term. Okay? So again, you get the linear combination of the V1 through Vk. Okay, so speaking of spans, we saw in our introductory video on vector spaces that the set of polynomials Pn of degree less than or equal to n is an example of a vector space. Okay, so we saw in our last video that Pn can be written as the span of the monomials 1x x squared through xn. Okay, so let's start from the very beginning. Okay, a very good place to start. Is there a P0? Yes, because we can make an x to the power 0, which of course is the constant 1. Okay, so it's just the span of a constant 1. Well, all multiples of 1 are just that multiple, which means that it's just a set of real numbers. Still kind of boring, right? But there is a P1, and that will now be the span of 1 together with x. Okay, so these are now the linear polynomials together with the constant polynomials. We can keep going. So we can have P2 up to x squared, all linear combinations of 1, x and x squared, P3 up to x cubed, and so on. Okay, well, so it's pretty obvious that this span is inside this span, okay, because 1 is also here, and this span is also inside this span, okay, because 1 and x are in this spanning set for P2. So we can say that P0 is a subspace of P1, P1 is a subspace of P2, and P2 is a subspace of P3, okay? So we call this an ascending chain of subspaces. All right, so obviously this doesn't have to stop at P3. We can make P4, and every polynomial in P3 is also in P4. So in general, if we have made Pn up to x to the power n, we can include one more power, the next power. So we get Pn plus 1 as the span of 1, x, all the way up to xn, and also xn plus 1. All right? So this ascending chain or this ascending sequence does not have to end. Okay? It can keep going. And so P0 is inside P1, which is inside P2, and so on. But surrounding all of those vector spaces is one enormous vector space, which we will call P. There is no superscript. Okay? Who is this P? Well, as you may guess, it's everybody. All polynomials in the variable x. Okay? So let me tell you at this point that if you're following along, we went from 4.1 to 4.2, and then we skipped over 4.3 and 4.4, and now we're in 4.5, talking about subspaces. Okay, what did we skip over? All right, so in a nutshell, it is possible to talk about infinite sets of vectors in linear algebra. Okay, so here I have the monomials 1x through x to the n, but these dots, these tell you that the list keeps going and does not stop. All right, so if you remember from your calculus, usually the second semester, we talked about sequences and series. Okay, so you can think of this set as an infinite sequence of monomials that never ends. Okay, what does the span of that set, that infinite set, look like? Well, fortunately, as we say in 4.4, you only have to worry still about finite linear combinations. Okay, so in linear algebra, we don't talk about infinite series of vectors expressed basically as linear combinations. That's not part of the realm of linear algebra. That's in a more advanced field, which is called functional analysis. Okay, and as the name implies, you do that to functions treated as vector spaces. We will probe on this a little bit, but we won't go really deeply into it. Okay, so this is the part that we're going to do. All right, let's go back to function spaces. We said that the vector space capital F of I is made of all the functions f of x, so that f of a is defined for every a in our interval I. Okay, so it's basically all the functions whose domain includes I. Okay, could be bigger than I, but it has to include I. Now, speaking of calculus, let's talk about special families of functions. So probably in the second week of calculus, we start talking about continuous functions. Okay? So let's denote by C of I all the functions in f of I, so that f of x is continuous on the entire interval I. Okay? Why is this a vector space? Well, non-empty, it must have the zero vector, it must be closed under addition, and scalar multiplication. Okay, is the zero function continuous? All right, so remember back in 4.1, we said, oh, what does it look like? It's just the x-axis, a horizontal line. That's a continuous function. Is C of I closed under addition? Well, what do we know from calculus? If you add two continuous functions, then their sum is still continuous. If you multiply a continuous function by a number, a scalar, constant, it's still continuous. All right, so we have the two closure properties. So about the third or fourth week of calculus, you start talking about the derivative, okay? And you talk about differential functions. So we said also that every differentiable function is also continuous. Okay, but first we will write as C1, set of all functions f of x from the interval so that f of x is differentiable. Okay, but we will also require one more condition. We want the derivative to be continuous on the interval. Okay, we'll see more about that in a little bit. Okay, but since every differentiable function is also continuous, then the set of all first differentiable functions, C1, is a subspace of continuous functions. Okay. Oh, you know what? Let's back up a minute. Closure and zero function. What's the derivative of z of x? Does it have a derivative? Yes, it does. It's still z of x. Okay. If you add two differentiable functions, is it still a differentiable function? I keep missing the b. Yes, it's still differentiable. Okay. If you multiply a differentiable function by a constant, is that scalar product still differentiable? Yes, it is. Okay. So we have C1 is a subspace of all continuous functions, Ci. Okay, but what about fourth or fifth week of calculus? Talk about the nostalgia trip. You talk about second derivatives, higher derivatives. Okay, so we can talk about twice differentiable functions, and we want the second derivative to still be continuous. Okay, so again, zero function, yes. Can you add them? Yes. Still closed. Times the scalar. Still closed. But why is it that C2 is inside C1? Okay. Well, if we're requiring up to a second derivative, and it has to be continuous, well, of course, the first derivative, number one, had to exist. Number two had to be differentiable. Okay. So therefore, every twice differentiable function has to be itself differentiable with just one derivative. Okay, so C2 is now a subspace of C1. C1 is a subspace of C. And yeah, if that's a C1, should this be C0? Yes, we sometimes write it as C0, just continuous functions. So kind of like how we had P0, although the meaning here is very, very different. Okay, here it just means continuous functions. So I hope you notice we started with this space and then it got smaller. This is the ambient space. This is a subspace. And there are, of course, many functions which are not continuous. Okay, so this is a proper subspace. Okay, are there continuous functions which are not differentiable? Yes, the absolute value function, for example, the v. Okay, it has a corner, so therefore there is no derivative at 0. Okay, and so on. Okay, there are functions with a first derivative but don't have a second derivative. But every function that does have a second derivative it had to have a first derivative. Okay, so it's getting smaller. right? There are fewer and fewer functions, and so the picture is going to look like this, okay? And we have C2 inside C1. We will have C3 inside C2, okay? So we can talk about functions with n derivatives, and the last derivative has to be continuous, okay? But back when we were in calculus, we have seen lots of examples of functions where you can take as many derivatives as you want, okay? So what are some examples of those functions? Well, we were talking about the polynomials, right? So all of Pn, all of P, can have as many derivatives as you want, okay? So all polynomials, okay? What else do we know from calculus? Trig functions, sine, cosine. And of course, you can compose, you can do sine of 3x, okay? What else? Well, maybe a little bit later, we talked about the exponential function, okay? So all of these, and again, you can compose. All of these functions, you can take as many derivatives as you want, okay? So they belong in C infinity. All the functions where you can take as many derivatives as you want, okay? So that is an enormous, enormous function space sitting inside all of these other subspaces. All right, so why did we require the C1 functions to have not just a derivative, but also we wanted this derivative to be continuous, okay? Well, that's because in chapter 5, we are going to generalize the idea of a linear transformation, okay? So the derivative will be an example, a very important example of a linear transformation. We can take a function with a first derivative and take the derivative of that function. But if we require it to be continuous, then it will go to the set of continuous functions on that interval I. Okay? So of course, more on this when we get to the next video, where our goal in those next 4 videos after this one is to use the techniques of linear algebra to solve differential equations. Okay, so let's go on to the next vocabulary word in our objectives for this video, and that is for a basis for a vector space. A set of vectors B from a vector space V is a basis for V if B is linearly independent and spans V. Okay, so this is the same definition essentially that we have for Rn. We will agree that the zero vector space V consisting of only one vector, a zero vector, does not have a basis because any set which contains the zero vector is automatically dependent. So there's no way that we can get an independent set out of just this one limited choice. Okay, so the easiest example would be, of course, for our Pn spaces, our polynomial spaces. We said that Pn has these special monomials 1x through xn. And in the last video, we said that we can write Pn as the span of these vectors, but they're also a linearly independent set. Okay. In general, we said that if a set of polynomials has different degrees, one of the last theorems in that last video, then that set is automatically linearly independent. Okay, so therefore, this B sub n is a basis for our P. All right, so now we come to an important theorem, which is actually very, very short. It basically just says that any non-zero vector space V has to have a basis, at least one basis. Okay? It sounds so short and so simple, and yet sadly, this is one of the few theorems in the fourth edition which we cannot prove completely. Okay? Here's what. Back in chapter 2, if you had a subspace of Rn, we used the extension theorem to grow a basis. All right, so how does it work? I'm not even going to bother writing anything down. Okay? Let's tell the story. So, once upon a time, we had a subspace W of Rn. So, there's at least one vector in that subspace because it's not empty. Okay, so close your eyes and pick a vector from W. Okay, so let's call that vector W1. Oh, wait a minute. V is a non-zero subspace, or vector space. Okay, so let's be more specific. Pick any vector except the zero vector. Okay, there's a non-zero vector there. So pick a non-zero vector, call it W1. Okay, is the set consisting only of that one non-zero vector linearly independent? Yes, because a set of one vector is independent if and only if it's not a zero vector. Okay, for the span of that single vector, you will be completely inside the subspace. But is it possible that you're filling up the entire subspace? Well, if you are, then you're finished. The span of that one vector is your subspace, and it's independent, so therefore it's a basis. Okay, but what if you're not filling it up? So there is at least one vector in the subspace which is not from the span. Okay, so close your eyes and pick that another vector, call it W2. It's obviously not the zero vector because the zero vector is always in the span. So if you're outside the span, it's not a zero vector. So now you have two vectors from your subspace. If you put them together, is that an independent set? What did we say? A set of two vectors is independent if and only if they're not parallel. Okay? Well, if the second vector is not in the span, it's not the scalar multiple of that vector. And neither of them is the zero vector. Okay? So therefore, they can't be parallel to each other, independent. So we can do the same next step as before. Let's now find the span of those two vectors. Okay, we get something like a plane in our vector space. Did you fill up the entire vector space? Well, if you did, then you're finished. But if you didn't, guess what? Pick a third vector. Okay, so I hope you see the idea. You keep growing this set of vectors, W1, W2, maybe you need a W3, maybe you need a W4, and by the extension theorem, the bigger set, the enlarged set, is still independent. And of course, the extension theorem remains true in an abstract vector space. So, you can keep asking the question, are we done yet? Are we done yet? Did we cover the whole space? Did we fill up the entire space? That's where the problem lies in chapter 4. Okay? In chapter 2, we said that if you have n plus 1 vectors in Rn, your set is automatically dependent. Okay? We have no such breaking mechanism for an arbitrary abstract vector space. Okay? Our algorithm in chapter 2 had to end with at most n vectors from our subspace serving as a basis for a subspace. Here, we don't have such a breaking mechanism. Okay, so to complete the proof, we need a very powerful lemma. It's called Zorn's lemma, and it is also known as the axiom of choice. Okay, it's also known as a method called transfinite induction. Okay, so of course, this is like induction, but it's on steroids. Okay, and yeah, it's a big can of worms. So suffice it to say that we will believe that every non-zero vector space V does have a basis. All right, so our final concept is the concept of a dimension, the dimension of a vector space. Okay, so that problem that I talked about, that we don't have a breaking mechanism, now gives us vector spaces which we say are not finite dimensional. Okay, so let's look at this. A non-zero vector space V is called finite dimensional if we can find a finite set B which acts as a basis for V. We call such a set a finite basis for V. Otherwise, we will say that V is infinite dimensional. We will agree that the space made of only the zero vector has dimension 0 and is therefore also finite dimensional. Okay, so now we are going to focus strictly on finite dimensional vector spaces. We'll mention an example of an infinite dimensional space in a minute, but we're not going to take it too seriously. Okay, any two bases for a finite dimensional vector space must have exactly the same number of elements. We call this common number the dimension of V, and it is denoted as dim V. Of course, we pronounce it as dimension. If the dimension of V is K, we also say that V is K-dimensional, or V is a K-dimensional vector space. All right. So yeah, so it's just like back in chapter 1 and 2. Okay, a line in Rn is a one-dimensional subspace. A plane in Rn is a two-dimensional subspace. All right, let's talk about the polynomial spaces. So we said that Bn, the set of monomials 1x through x to the n, is a basis for Pn. Okay, so what is the dimension of Pn? How many vectors are in here? So we kind of mentioned this in our last video. Okay, you might be tempted to say it's just n, but no, that's x to the 2, x to the 1, x to the 0. So therefore, there's an extra vector, and that dimension is n plus 1. Okay, so of course, Pn is an example of a finite dimensional vector space. Right? So if you remember the pretty picture, we said that all of these polynomials go into this ginormous vector space, P, made of all the polynomials. Okay? So again, in that section that we skipped, 4.4, okay, we would have seen that this set B, consisting of all the monomials, keep going. It's an infinite set, but it is linearly independent still. And this tells us that this set spans P. Okay? So therefore, this B over here is a basis for P. What is its dimension now? Well, 4.3 would have told us that this set here has an infinite cardinality, an infinite size, but that infinite size has a name. Okay, it's this funny symbol over here. That's the Hebrew letter Aleph. Okay, so this is Aleph 0, sometimes pronounced as Aleph naught. Okay, that would be N-O-U-G-H-T. Okay? So we will say that the dimension of the space of all polynomials has dimension Aleph not. Alright, so just 5 minutes ago, we said that any subspace of Rn must have a basis and it can't have more than n vectors. Okay? So, what does that mean? Any subspace of Rn has dimension at most n. Okay? So this is true in general. If W is a subspace of V, then the dimension of W has to be less than or equal to the dimension of V. If V is a finite dimensional vector space, the statement is no longer true for infinite dimensional vector spaces. That's why one of the reasons why we're avoiding that big, literally big can of worms. Okay? If you take a higher division math class, I hope you take functional analysis. You will learn a little bit more about this issue. We'll talk about Hilbert spaces, Banach spaces, and all sorts of amazing things. Okay? So, furthermore, the dimension of W is the same as the dimension of V, if and only if they were the same space. Okay? And again, this theorem is not true. This equation is not true for infinite dimensional vector spaces. Okay, so finally, we're going to get our hands dirty and we are going to study this set of polynomials from P3. We are going to show that this W, as the letter implies, is a subspace, so it has to satisfy the 3 conditions. We will find the basis for the subspace and we will state its dimension. Okay, so the polynomials in W are the polynomials in P3, where if you plug in -2 into the polynomial, what you get is 4 times what you would get if you plugged in 1 into the polynomial. And furthermore, there's one more condition. If you take the derivative of the polynomial and you plug in 3, you should get 0. Okay? So, non-empty property. A subspace should always contain the 0 vector. Okay? The 0 polynomial in this case. What happens if you plug in -2 into the 0 polynomial? What answer will you get? It's not -2, you will get 0. That's why it's a z. What would you get if you plug in 1 into the 0 polynomial? You will again get 0. Okay? So is the first equation satisfied? Is 0 equal to 4 times 0? Go back to chapter 0. Yes, of course, that's true. Okay? Second condition, the derivative. Does the 0 function have a derivative? Yep, we mentioned that a short time ago. It is still the 0 function. Didn't go very far. So if you plug in 3 in here, it's the same as plugging in 3 in here, which is going to give you 0. So yes, the second condition is satisfied. Okay? Next, is W closed under addition of polynomials? Okay? So let P of x and a second polynomial, Q of x, be from P3, and not just from P3, but from W. Okay? So what does that mean? If P of x is from W, then these 2 equations have to be satisfied. Okay. We must have that equation, those 2 equations, satisfied. Let me make some more space. However, so is Q of x. So not just P, but also Q has to satisfy these two equations. So all we do is replace the letter P with the letter Q. Okay? So now Q also satisfies these two equations. What are we trying to do here? We must show that the sum P of x plus Q of x should also be a vector in W. Okay? So in other words, P of x plus Q of x must satisfy these two equations. Okay. So what we have to do is we should replace P with P plus Q. And we must show that these two equations are still valid. Okay. So we must show that this equation is true if we replace P with P plus Q, and same thing over here, and same thing over here. Okay, however, we know our algebra, don't we? So, start with the left side, okay? What is the meaning of that? It means P of minus 2 plus Q of minus 2. Okay? Do we know anything about those? Yeah, they're right here. P of minus 2 is 4P of 1. And Q of minus 2 is 4Q of 1. Does that look like this? Yeah, I suppose we can do one more step. We can say that this is the same as 4 times P of 1 plus P of 1, factor out 4. And now we can say that, yes, that looks pretty much like 4 times P plus 2 evaluated at 1. Awesome! So what about the second equation? Okay. Well, what is the formula from calculus? The derivative of a sum is the sum of the derivatives. So that's P prime of 3 plus Q prime of 3. Gosh, do we know anything about those? Oh, they're right here. P prime of 3 is 0, and Q prime of 3 is also 0. Boom. Okay, so therefore, P plus Q satisfies the second equation as well. All right, what about scalar multiplication? So, what do we have to show this time? Instead of these two equations, we must show that the equations with Kp are also satisfied. Okay, so replace P with Kp, and same thing over here and over here. Okay, who is this K for any scalar? K. Okay, so again, do we know what these mean? Well, this means you take K and then you multiply it to P of negative 2, which I will copy from here. Do we know anything about that? Yeah, it's from the same equation over here. So that's K times 4 P of 1. Okay, what can we do there? We can move 4 to the front because of this little thing called associativity. 4 K of P1. K times P of 1. Okay, so yes, that is exactly the same as 4 times the function K times P evaluated. at 1. Okay? And similarly, of course, the second equation can be rewritten as, from our rules of derivatives, k times p prime of 3, which I will steal over here. But do we know something about p prime of 3? Right there, it's 0. 0, anything times 0 is still 0. So therefore, k times p satisfies the second equation. Okay, so we are ready for the main event. We are going to find a basis for w. So the idea here is we can use the standard basis for our ambient space. Right? So here's the definition of w. It lives inside P3. Okay? So this is the reason why it's important that we specify who the ambient space is for W. If it were in P, we would have a big problem. Okay? That would not be a finite dimensional space. Okay, but we said that our basis is 1x squared x cubed. Okay, so thus we can write P of x completely. It can be expressed as a polynomial. So we can write it as C0 plus C1x plus C2x squared plus C3x cubed. Okay, that is somebody from P3. Okay, so now P of x must satisfy these two equations. Okay, so first let's see, what is P of negative 2? Okay, so we have to replace x with negative 2. So that would look more natural as minus 2c1. Minus 2 squared is 4, so that will be 4c2. Minus 2 cubed is minus 8. So that can be written as minus 8c3. Okay. What about 4p1? Okay, so yeah, we can include the 4. So it will be 4 times. So we do the same thing. Replace x with 1. Okay, now that's going to be a lot easier. Okay, so 1, 1, and 1. Okay, so the first equation forces an equality. It says that this must be equal to this. Of course, that can be written as, let's distribute 4c0, 4c1, 4c2, 4c3. So let's see, yeah, I think let's move everything to the other side. So therefore, 0 equals, how many will we need? So 4 minus 1, 3c0, 4 plus 2 becomes 6. 4c2, oh, c2 disappears. Okay, 4c3 plus 8c3 is going to be 12c. Ooh, okay, and look, check it out. Something else happens, or simply 0 equals, check it out, we can divide everybody by 3, and something wonderful happens. It's 2 and 4. Okay, so the coefficients of p of x have to satisfy this equation, forced by this first condition. Okay, so similarly, we have to satisfy the second equation. So we will need p prime of x. Okay, so from here, Everybody knows how to take a derivative, right? The constant disappears. C1x becomes C1. Derivative of x squared, 2x. So we drop the degree, and it's 3x cubed, so 3x squared. Okay? So the second equation forces, we want p prime of 3 to be 0. And I should have prime over there. And so, what do we get? Plug in 3 in here. And what's gonna happen? 3 times 2 becomes 6. 3 squared is 9 times 3. We get 27. Okay, so that's the descriptions force the coefficients to satisfy our first equation over here. And I'm going to write it more naturally as this equals 0 and this equals 0. I so wish I could see the look on your faces. Does that look familiar? Of course, we've seen that before. That is a system of linear equations, and it's a special kind. It's a homogeneous system of equations. Okay, so we must solve this homogeneous system. Okay, if only we had something that will help us solve this. Okay, 2 rows, and we have 4 coefficients. Okay, we don't need the zeros. All right, I'm going to skip that 0, just 2 by 4. Okay, so C0, 2C1, no C2, 4C3. Okay, I caught it just in time. No C0, 1C1, 6C2, 27C3. Check it out, it's almost reduced. Yeah, it's already in row echelon form, but it's not reduced because of the 2. So all we have to do is subtract twice the second equation from the first. Compute matrices RREF. There we go. Ooh, nice integers. Yes, of course. Okay. So therefore, we have 2 leading variables, C0 and C1. Are leading, and C3, C4, 4, I said 4, are free. Okay, so we know what to do. Solve for the leading variables in terms of free variables. So C0 equals 12C3 plus 50C4. Okay, and who is C1? C1 must be negative 6 C3 plus, no, minus 27 C4. Okay, excellent. So what do we do with that? Okay, now what? Ooh, we know how to solve systems. Whoopee! What's it good for? Well, where did they come from? They came from right over here. Okay, but p of x is this guy. So we can now plug this in. C0 is this. Replace. C1 is this. So I better put parentheses right here. There we go. Okay. There is, oh, I'm sorry. That should be, it's like, wait a minute, I'm missing something. That should be C2 and C3. Okay. When you were watching this, you're probably like, okay, when's he gonna notice that something's wrong? There we go. C3. And I had enough coffee. So this should be C2, C3, and right there. And this is C2 and C3. There you go. Okay. So I started to notice because what I was about to ask is, so what symbols, what coefficients do we see over here? Okay. So we only see C2 and C3. Okay. So therefore, we can rewrite this as, we can factor out a C2 and we can factor out a C3. Okay, so what goes with this? With C2, I have a 12 from over here, a minus 6x from over here, and an x squared from over here. Okay, it's just all accounting. Make sure you get all of the terms. C3 has a 50 over here, and then you have a minus 27x from over here, and we have x cubed over here. Okay, great. We know how to factor out C2 and C3. Okay, big deal. Now what? Well, big picture. We started out with P of X from P3, and we said if P of X is in W, P of X is the coefficients are forced to satisfy this homogeneous system of equations, which forces C0 and C1 to have these values. Okay, and now we see that P of X is a multiple of this polynomial plus a multiple of this other polynomial. Ooh, does that look like something we have a name for? Yeah, that's a linear combination of those two polynomials. Okay, so this tells us that every P of X, which is from W, must be a linear combination of these two polynomials, which we will now put inside a set. Okay, and oh, wait a minute. This gives us the spanning property. Okay, so that let's call that B. Wonder why we're calling it B. So W is the span of B. Okay. The degree of this polynomial is 2. The degree of this polynomial is 3. They're different. Okay. So this set is linearly independent, since the degrees of the polynomials in B are distinct. B is independent. Okay, and that property is, of course, very useful in other examples where you might have 3 or 4 polynomials in your spanning set. Okay, if the degrees are all different, and they will be, yeah, that set will be independent. Okay, so therefore, B is a basis. Ta-da! Okay, what is the dimension of W? The easiest part, how many vectors are in it? 2. Okay, so W is a two-dimensional subspace of P is 3, P3 is 4-dimensional. There we go, yippee! So that is our video for today. Thank you very much for watching. This is True Socrates signing off. You'll find me on Facebook. You'll find the 4th edition on Facebook, and of course at kendallhunt.com. So until our next video, when we introduce linear transformations, I hope you enjoy the rest of your day.